lectures of Tuesday and Thursday this week. And he's not here today because he's in Austin, but he'll be on Thursday. And next week, it will be another person that will give the lecture on Tuesday. I'm sorry for my accent. I have a strong accent from my country. I come from Brazil. And also for my English that is very poor. I ask you for excuse me for my pronunciation errors and also to correct my pronunciation errors, if you don't mind. And I try to speak slow for you to understand, but if there's any problem, you can ask me. My lecture will be about MOSFET modeling, addressed for low voltage and low power IC design. Today, let's start here. Today, I will talk almost only about modeling, but on Thursday, I will try to give some examples of analyzing and designing circuits using the models I will present here. Okay? Are you understanding me? Okay. Well, for today, I will give a short introduction. I will discuss the problem of choosing the terminal which will be the voltage reference in the model. So we'll review a little bit of physics concerning the charge distribution in a MOS transistor. And then I will present these two models, the EKV and the ACM models that are charge-based models. Both are bulk referenced models. And next Thursday, I will talk about short chain effects, and I'll give you the examples I promised. I hope so. I don't know many things, but I hope I will give you some useful information. Well, let's start with the obvious. Um, Low voltage circuits will need really uh, that the devices operate with low levels of inversion. I mean, you are used to make your hand calculations to the designs using the a strong inversion model, that is the quadrant law equation between voltage and current. But when we work with low voltage, we'll need low inversions. We use to we'll need to use low inversion levels. And for example, in this circuit, if the voltage drop between these two terminals is low, that is VDD minus VSS is low, and I have to, for example, to put these two transistors in saturation, I will need to have the VDS drop between the terminals high enough, and to do this, the VG voltages must be small. And if I decrease the VG voltage, maybe these two transistors will go to moderate or weak inversion. Okay? Did you understand? Also, for the case of low power, it's obvious that if I have fixed VDD minus VSS, the current, the drain current must decrease, and to have a small drain current, I can either diminish the aspect ratio, but I have limitations for this because each technology has a minimum width, and also if I increase the length, I will have limits in frequency operation. It must be necessary perhaps to decrease the value of VG, and also to put the transistors in weak or moderate inversion. The moderate inversion is still more difficult to model, isn't it? But you can do it. If there's any doubt why using weak or moderate inversion models, let's also mention that if you try to design a circuit using a strong inversion model, but your circuit will operate with low voltage or low power, and so your devices will be in weak or moderate inversion, we will fail to predict the performance properly of the circuit. Okay? There are some circuits that are designed taking advantage of the exponential behavior of the transistor in weak inversion. And so, how can you use a strong inversion model to analyze or to design such circuits? You must use a weak inversion model. And as a third thing I'd like to mention is that many circuits like amplifiers have their optimum performance regarding um, uh, power consumption and size and gain and many other things. They have the optimal performance in moderate inversion, and so you should design the circuits better using a model that is valid also in moderate inversion. Okay? Any questions? You may interrupt me because I may be excited, and so I can forget to ask you. Um, Now let's talk about the problem of choosing the terminal as a reference. I suppose you are used to use the source as reference because the most popular models use the source as reference, isn't it? Be seen, for example, is source as reference and other. But we can also use the book. There are models that use the book as a reference. I will tell you, it's not a matter of accuracy. Each model have both kinds of models. The bulk referenced or the source referenced models have equivalent accuracies. It's not a matter of accuracy, it's rather a matter of point of view. Okay? A matter of point of view. When you use a source reference model, you are emphasizing a point. Your point of view is emphasizing. Is it correct? The pronunciation emphasizing is emphasizing the control of the charge distribution by the transversal field. Okay, then you will uh, decide the not decide, but you will analyze the level of inversion by a comparison between the gate voltage and the threshold voltage. That is a parameter dependent upon the bulk voltage because of the bar effect. But when you use bulk reference models, your point of view will change a little. You will emphasize in your point of view the charge distribution along the channel. That is, you will emphasize the control of this charge by the channel voltage. The channel voltage is a sort. I don't know if you are used with this concept of channel voltage. Are you? Yes. Yeah. I would say as an intuitive mean that it is a measure of the imbalance. I can say imbalance. Imbalance. Imbalance of energy in the channel, because now you have a voltage drop Vd minus Vs, and so you have no more equilibrium, you have current, and in each point of the channel, this imbalance can be, I would say, measured by this channel voltage. Not measured in the sense that you put an instrument, but the channel volt will give an indication of this imbalance. But if it's too vague for you to understand, I can also say that if I could, I will use the paper. Please, will you change just for a moment? What can I do? Just for a moment, the papers, please. If I have an end of the channel fixed and I could move the other end, it doesn't matter if it's the source or the drain, okay? But if I can move it, but not altering the profile of the channel, keeping the same profile, then if I move this end of the channel, instead of, for example, if it is the drain, instead of VDB, I would have here another drain with the voltage VCB of this point X. Let's say this is X1. If I move a little bit more, I will have another drain, not with VDB, but with the voltage VCB x2. So that is the meaning of the channel voltage. It's an arbitrary meaning, okay? It's not a, it has a physical meaning, but then I would have to talk about the theory of energy band here. I don't remember this theory. It's very beautiful, but it's very difficult also. We need not to do this here because I think you are interested uh, rather in circuit design than the physics of the MOSFET. Okay? Then, now as I was talking, the point of view emphasizes the control of the charge distribution by the channel voltage, and so to analyze the inversion level, we will compare the channel voltage with another parameter, the pinch-off voltage, which is dependent upon the gate voltage. Okay? In each point of the channel may be in strong or weak inversion. That depends of the comparison of the channel voltage in this point with the pinch-off voltage. Sure, if the the pinch-off voltage would be the value of the channel voltage. Surely it is arbitrary because the transition is smooth, but it can be said to be the value of the channel voltage that separates the channel into a weak inverted part and um, a strong inverted part. Okay? Then I will summarize some advantages of its choice of a terminal for voltage reference. Uh, what I can say about the source reference models is that it's perhaps easier to work with them when you want to compare circuits with different devices. Because there is a similarity between the equations that you use in source reference models and the equations for three-terminal devices as bipolar transistors. These source reference models are also better suited for analysis when you want to start the control of the bulk on the over or on, I don't know, the channel. Okay, the case of the bulk of a second gate, and also to analyze the properties concerned to the current transport along the channel. The fourth thing, I wouldn't say it's an advantage. I would say that it's a limitation of the measurement procedures. I think nowadays the measurement procedures in RF are um, limited to three terminal devices. It's difficult to consider the four terminal devices, isn't it? I never made a measurement in RF, but people told me the equipment is not addressed to four terminal devices. And so, to be consistent, to use a model that is source referenced is better. As advantages of the bulk reference models, we have the symmetry of the device is more evident It's emphasized in the book reference model. The symmetry concerning the interchanging between drain and sources. Obviously, the symmetry exists when the layout is symmetric, because there are layouts that are not symmetric, but most of them are. The book reference models is more suited for analysis of weak inversion circuits and of the problem of mobility reduction to the transversal field, the vertical electric field. And I think as a fourth advantage is that the fact that the bar effect is not treated as um, a normal, a normal, not normal, a normal, abnormal thing. It appears naturally. Sure, because we are treating with the influence of VDB and VSB over the channel also as the influence of VGB. But each model that is source referenced can be converted in a model that is bulk referenced and also the contrary. So you must not be afraid with the choice you made. You can change it with not losing the accuracy of the model you are using. Any question? Just to illustrate, if you want to analyze a small signal model that's book reference, but you are used to the source referenced small signal model. Here is the most the mo here is the simpler. I think it's the simplest model that you can have for quasi-static operation. And we have 3 transconductance and 5 capacitance. It's not complete. For charge conserving purposes, it will fail. And so, but I only want to show you that in this branch here, the 2 currents must be the same. So if I equate them, I will find that the equivalence between the transconductances is this one. The the gate transconductance in the book reference model is the gate transconductance in the source reference model. The drain transconductance in this model is the output conductance in this model. And the source transconductance in this model, look at the detail, the current is in another direction. Is the sum of all 3 here. Okay? If you want to convert from one to another, you must do this. Any questions? Because now we'll go back to the physics of the MOSFET, but I want to be very quick here, not to bore you. Not that the subject's boring, not for me, but I think you are circuit designers who don't want to enter deep in the physics of the device. I don't know. But I wanted to give a justification for the models, and so let's go back to this physics just for a small moment. And I will start not with the complete MOS transistor, but the capacitor structure of the transistor. That is a MOS transistor with only 2 terminals. Let's suppose it's a p-type, okay? I forgot to put it here, but let's suppose it's a p-type. Then we have the voltage balance in this structure. requires that the applied voltage between gate and bulk is equal to all the voltage drops here inside the MOS capacitor. The gate is potential, but we have a voltage drop in the insulator, through the insulator, and also um, a voltage drop in the semiconductor. This is the phase potential, the potential that you measure in the interface between the semiconductor and the insulator, referred to a point in the substrate, the bulk, where we have no more charge. And finally, we have this voltage here, which accounts for the contact potentials between the materials, the different materials along the structure. Okay? And then our voltage balance is given by this equation. Our charge balance is given by this equation. We have the gate charge, the semiconductor charge, but also the parasitic charge in the interface between um, insulator and semiconductor that are due to the process of fabrication. Okay? Are you understanding me? Okay. Then, to simplify the things, we will define the flat band voltage as a voltage that accounts for these contact potentials and this parasitic charge. So we'll have this equation for the voltage balance in the MOS structure that relates the surface potential with the gate potential, the gate bulk voltage, and the semiconductor charge. All these charges and capacitance are per unit area. Okay, so these are density charges. Then we have the regimes of operation. Accumulation is the regime where the gate to bulk voltage is smaller than the flat band voltage, so that the charge in the gate will be negative and it will attract the holes. It will attract the holes to the surface. They will accumulate in the space. In the depletion regime, VGB is VGB minus VFB is positive, but not enough to invert the channel. Still not yet not enough to invert the channel, but it will push back the holes, push away the holes, and the ionized acceptor atoms will be uncovered, their charges will be uncovered. And so we have this depletion region here. Um, in this situation, the surface potential, that is the potential measured here in the interface, is positive, but is less than the firm potential. The firm potential can be understood as the contact potential between the doped and the intrinsic semiconductor. Okay? It's not that there is a junction like that here, but the concept of the firm potential is like that. The contact potential between the intrinsic and the doped material. And finally, you have the inversion, which is when this is review for you, but I cannot keep myself from talking about because of the things I will talk afterwards. The inversion, the space potential is greater than the Fermi potential. So we'll have an inversion just under the insulator interface with the semiconductor, and it's as if the material here is no more p-type but n-type, just in a small sheet under the insulator. Okay. Then I'm interested in the charge distribution. As I said, how I can compute this charge distribution. I must solve the Poisson equation in this material. But since I have voltage drops only in the vertical direction, I can reduce the Poisson equation to the one-dimensional case, which is easy to solve. And as it's the charge density, volumetric density in the material, I must evaluate this by evaluating the charge, sorry, the carrier concentrations with respect to the potential in the y direction, the vertical direction. So we have for the free electrons this concentration, for the holes, and for the ions, the acceptor ions, I have this concentration. We sum all them. These ones give negative charge, this one positive charge, and this will be substituted here, and then I will integrate this equation to have the uh, electric field in the vertical direction. And with this electrical field in the vertical direction, I use the Gauss law to evaluate the semiconductor charge. It's a little bit difficult no, it's not difficult, but I must use this mathematical relationship that is exact to solve this. And then I will have this equation. You can see that uh, the contributions of each kind of charge is very clear. We have the contribution of the holes, the contribution of the acceptor atoms, and the contribution of the free electrons. And we also can compare their magnitudes, in each case, accumulation, depletion, inversion, because of they are related to the values of the surface potential. Okay, then when the surface potential is negative, this exponential will predominate over all the other terms, and the wholes predominate. If the space potential is positive but still under the firm potential, then the holes will be negligible, the contribution of the holes, but the contribution of the free electrons is not important yet, and the ion charges will predominate. And then the inversion that is of our interest, we'll have both contributions of ion charges and free electrons. We may neglect this term here. We may use a simpler form of the semiconductor charge by neglecting this term here. And I will do this. But I will do this for the four-terminal MOSFET. Okay? For the four-terminal MOSFET, where I must also take into account the control of the charge by VDB and VSB. Sure. How can I do this? I will use the gradual channel approximation. The gradual channel approximation means that I can use the same equations, just introducing the channel voltage in the electron concentration. Sorry, the electron concentration. My tongue is not able to pronounce English, I think so. uh, You see, if I want to be rigorous, the Poisson equation in the case of the four-terminal MOSFET should be solved in its two-dimensional form, because now I have a transversal field and a longitudinal field, and so I would have to solve it in its two-dimensional form. But if I consider that the variations of the longitudinal field are much smaller than the variations of the transversal field, I can use the gradual channel approximation and solve the Poisson equations in its one-dimensional form, but making this modification, modifying the electron concentration, because it's very significantly influenced by the channel voltage. Okay? Then I will make this modification, and I will derive this equation for the semiconductor charge. As I'm considering only the inversion regime, I omitted the influence, the contribution of the holes. That's very small. It's negligible here. Um, but the drain current is directly related not to the semiconductor charge that has a depletion component and an inversion component. The drain current is related to the inversion charge density in the channel. So how can I evaluate the inversion charge density from this semiconductor charge density? Now I will use two more approximations. Most analytical models use these three approximations I'm using here: the gradual chain approximation, the depletion approximation, and the charge sheet approximation. Most analytical models. If you want more accuracy than this, it's already very accurate, but if you want more accuracy than this, you must use a two-dimensional or three-dimensional model. Which are the models that you can find in the 2D or 3D simulators, the device simulators. Okay? But I'm interested to show you hand calculations equations that must be analytical equations, and so we will put all these approximations. Till now they are very accurate. The depletion approximation means that we can use in the inversion regime the same equation of the depletion region to compute the depletion charge density. Okay? The semiconductor charge density in the depletion regime, when we don't have electrons in the surface, is only due to this term here, the potential surface, the square root of the potential surface. So I will assume that the depletion charge here in the inversion regime is given by this equation. And by doing this, I'm also assuming that the surface potential is the same potential under the inversion layer. It's the same potential in the top, in the bottom, and in the top of the inversion layer, because the inversion layer is so thin solving that there's no voltage drop across it. It's an approximation, sure. It's the charge sheet approximation. I mean that the the inversion layer is a sheet of charge. So I can say that the voltage drop in the semiconductor is responsible for the depletion charge. And if I have an equation like this for the depletion charge, and I know that the depletion charge plus the inversion charge is the total semiconductor charge, I can have my equation for the inversion charge, where it is function of gate voltage and surface potential. And the surface potential, in the other hand, by using this equation and this equation, if I equate them, if I equate is the term. Okay, if I equate them, will be given by this expression. It cannot be evaluated analytically, it must be evaluated numerically, but you can compute the surface potential as function of the gate voltage and the channel voltage to finally have the inversion charge density as a function of gate and channel voltages. Now we finish the physics and we are going to the modeling itself. But first, I'd like to show you the behavior of the inversion charge density given by this expression. If I solve numerically the space potential in terms of Vd and Vcb, the behavior is like that. In strong inversion, I will have the inversion charge density as I want to say linear, because linear means passing by the zero. How do you say that? A first order polynomial, I could say like that. It's a first order polynomial, either of VCB as of VGB. I didn't show for VGB here because, as I told you, the models I will present are both bulk referenced. So I prefer to show the variation along the channel. Okay, it's the variation along the channel, and we have straight lines when where the channel is strongly inverted, and where the channel is weakly inverted, I have an exponential behavior. Okay, for the inversion charge density. These behaviors are observed if you use these three very accurate approximations: gradual channel, depletion, and charge sheet approximations. A classical definition for the pinch-off, as I told you, the pinch-off is the value of VCB where the channel changes from moderately inverted to weakly inverted. So I can say that this occurs when the surface potential equals twice the firm level, the firm potential plus the channel voltage. It's an arbitrary definition because the transition, everyone knows, is smooth. Is we can have many definitions for pinch-off, but they must be the same in neighborhood, sure. And this is the classical definition, and we can have expression of the pinch-off voltage in terms of the gate voltage if you apply this definition to the expression of the surface potential. Okay, if you solve this, we'll have this expression of the pinch off voltage in terms of the VDB. And you can note that the dependence of VP uh, on VDB is almost a first order polynomial. It's not a first order, but it's almost, because I have the square root and then I have the second power. It can be observed graphically only in the weak inversion. This curve will bend significantly. In the other points, it's almost a straight line. So for you that are circuit designers, we can use this approximation. This is a very good approximation for the pinch-off voltage. If you assume that this parameter n, which in fact depends upon gate voltage too, but very slightly, if you assume that it's constant, you have a very nice and simple expression for the pinch-off voltage in terms of the gate voltage. Here, Vt0 is the threshold voltage in equilibrium, that is for Vsb equal to 0. Okay? And n is a number that is close to 1. It's something between 1 and 2, but in moderate and strong version, it's something between 1 and 1.5. I like to use 4/3 or 1.25. It depends on the technology. Sure, you can extract it to have a better uh, fitting value, and if you want to use a constant value. But for circuit design, it's advisable to adopt this simple equation. Okay, and let's go to our long channel MOSFET modeling before we add the charge channel effects. Any questions? Okay. First, let's do something with the drain current expression. Another way of viewing analyzing the drain current expression. Everyone knows that no matter which semiconductor we are dealing with, the drain current can always be decomposed. Decomposed? I always look at me to ask for my English doubt. But it can be decomposed into a drift and a diffusion current. And these components are dependent upon the point of the channel. That is, they vary along the channel, but the total current is constant. The total current does not vary with the position along the channel, so we can integrate this equation to have the drain current. When we integrate this, we will have, as a result, an expression that depends on the situations in each end of the channel. Sure. The expression will depend upon the values of the charge density at the source end and at the drain end, and of the values of the surface potential at the source end and at the drain end. So we can write the drain current as the difference of two similar functions. These two functions are they have the same form. These two components here have the same functional form, And the only difference is that one is dependent upon the source voltage and the other is dependent upon the drain voltage. If you neglect the short chain effects, sure, after we put the short chain effects, we cannot do this. But we use this as a core model and we add the short chain effects afterwards. The component that depends upon Vs we will call the Ford saturation components because when Vd is enough great, this term will vanish. In the reverse saturation, it's the contrary. This term will vanish and we'll have only this one, which is the reverse saturation component. Okay? Then no matter what model you are using it, if it's a long channel device, it will be valid if your model is enough accurate. But what does it mean when I do this? What does it mean? It means that since the functional forms of both components are the same, I can characterize the device in the saturation regime. Okay? I can choose a saturation regime, either forward or reverse, and characterize the device because this other component will have the same form. And so I show you here these the circles, the small circles are measured values, so you can rely on my results. If I plot the common gauge characteristics, which are the drain current versus the source voltage with steps given by different values of the gate voltage in saturation, then I will notice that the square root of the drain current is uh, first order polynomial of the VSB. It also applies to the VGB, okay? The common source characteristics. Then in strong version, I have this behavior. In weak version, both uh, with respect to VSB or to VGB, I have an exponential behavior. This is no news for you, okay? This is no news for you, but this settles the asymptotical approaches for the drain currents, which must be respected by all models. All models must respect it, or it will be a very poor model. That in strong version, its saturation component is a second order polynomial of the voltage Vg, Vs or Vd, and Vb, and in weak version, an exponential function. And the difference between the models will be in how they approach the moderate inversion, the transition. Okay? And so we will see now how the two models I want to present you, the EKV and the ACM models, do this, how they approach the moderate inversion. Okay? Both are charge-based models, that is, they are derived from the charge density equations. That's why I put so much time in talking about the distribution of charge in the MOSFET, the semiconductor. Both are bulk referenced models, and both are single equations models. That is, they have a single equation for each large signal or small signal characteristic for the whole inversion regime. Okay? They don't have an equation for. They have surely the asymptotical behaviors like this exponential and second order polynomial, but they use a single equation for everything. Let's begin with EKV model. Let me breathe first. uh, let's begin with the EKV model, which was developed by a Swiss group, a group from Lausanne, from the EPFL, which means in French, École Polytechnique Fédérale de Lausanne. Uh, I think the EKV model had a very important role in the MOSFET modeling. I don't know if they were the first ones to do this, but at least they were the first ones to develop a entire model using the bulk as reference, and also to make this model popular. I don't know if they were the first one, but they had this merit. I can say this merit. This word exists. Okay. Then EKV, for your knowledge, are the initials of the three people that developed the model: Ens, Vitor, and Krumenacher. Okay, that's the reason for the name. Um, the KV model started from another form of the differential equation of the drain current. This uh, other form uh, relates ID to the derivative of the channel volt with respect to the position in the channel. How they, not they, this is a known equation. It was not created or discovered by them. It's very old. But from where it comes from um, the differentiation of the um, electron concentration. If you differentiate with respect to X the electron concentration, and reminding that the inversion charge density is the electron concentration multiplied by the electron charge, you have this because this term will cancel with this term. So this simple equation takes into account both diffusion and drift. It's exactly equivalent to this one here. Okay? Now, what the EKV trio had done, they expressed the inversion charge density as functions, as approximate functions of the channel voltage, and they integrate this expression with respect to the channel voltage. Now we will recall, I've shown you this before, that in strong version this relationship is first order polynomial, and the EKV used this approximation. You see that there is the pinch-off voltage here. So the dependence upon gate voltage is inside the pinch-off voltage. And in weak inversion, they use this exponential approximation. This potential here it is related to the pinch-off condition. And as pinch-off is a little bit arbitrary, it can be adjusted. We will see that they adjust it to have a nice expression, a nice fine expression for the current, but it's related to the pinch-off. Now, I have to integrate it, these two expressions, with respect to the channel voltage, but to have more explicitly the saturation, forward saturation, the reverse saturation components, we separate this integral into these two integrals, okay? And then we have these two asymptotical approaches for the drain current. But I told you that they use a single expression. Yes, they will use a single expression. Wait. Um, to do this, they applied to this to this strong to the strong version and weak version approximations. They applied an interpolation function. Okay, they applied an interpolation function which must have this behavior in the extremes of V. V and I are normalized voltages and currents respectively. I normalize the ET saturation component with respect to this specific current, which take into account the technological information and the geometrical information of the device. The specific current used in the EKV model, but also in the ACM model, as we will see soon. This current is the most important parameter of the MOSFET for circuit design because it has all this information, geometrical and technological, inside it. Then with IS and VT, you can do almost everything in hand calculations. Okay? Then you can notice that this current appears in both asymptotical approaches. If I come back, if I go back, it appears here. I just multiplied by the second power of it, of the thermal voltage, phi t, isn't it? And it's not clear here, but if I adjust the value of phi 0, it's phi 0. If I adjust the value of phi 0 accordingly, I can have the same factor here as here, and that's why I've written these equations in this simpler form. Okay, but I didn't show you yet the interpolation function. I want to show it now because they could do better. Using an interpolation function for the relationship between current and voltage, the accuracy is not so good as if they used an interpolation function between the derivative of this relationship. And so they presented interpolation function like this, but they preferred to use interpolation functions, an interpolation or a set of interpolation functions that relates the transconductance to current ratio to the current. Okay? Let's see how the transconductances behave. The source and drain transconductances have different behaviors in strong and weak inversion. Surely, um, they have a behavior similar to bipolar transistors in weak inversion, and they are dependent on the square root of the uh, saturation components of the currents in strong inversion. Normalizing the transconductance to current ratio, we will have this. Um, this is IS, the specific current. If I divide IS by each of the saturation components, I will have the normalized saturation component. So my interpolation function for this quantity, for this variable, must be something like this. Must tend to the inverse of the square root of the normalized saturation component of the current in strong inversion, and mass tends to 1, or that is, it's independent of the current in deep in weak inversion. Now, if I have an interpolation function that applies to this ratio, I can easily find an interpolation function for the relationship between voltage and current by integrating it. Okay? Questions? No questions. Well, then EKV people reported these three till now, these three interpolation functions. This first one is directly for relationship between current and voltage, and is not very accurate, but it has a good accuracy, but it has the advantage of being inversible. I can have either I as function of V or V as function of I. At the same time, they presented this interpolation function for the ratio between transconductance and current. From this one, they integrate in this, they derived, it's very ugly, but they derived these relationship for voltage and current. And finally, after some years of developing and studying, they decided that the best interpolation function would be this one for the transconductance to current ratio, and so the relationship between voltage and current is simpler. Okay? And it's nice. It has a term that's dependent on square root of current, and a term that is dependent on the logarithm of the square root of the current. And unfortunately, it's not inversible, okay? But it's nice, and it's very accurate. Okay, I have still 15 minutes to talk about ACM model. ACM is Brazilian model. Brazilian model, and is also bulk referenced. ACM comes from Advanced Compact MOSFET model. The name has a long story. I promise I will tell you if I had time on Thursday. But till now, let's assume that's Advanced Compact MOSFET model. And I must tell you that both models converge to almost the same thing at the end. But SM began by um, was first inspired by EKV, and because of this, they used they adopted the bulk reference and also the approach of separating the current into forward and the reverse saturation components. They in this aspect they started in the same way. ACM inspired by EKV. EKV went first. But the contribution of ACM is to give a physical basis to the model because, as you could see, the interpolation function was mathematically derived without physical basis. But ACM started everything from an approximation, which is the basic approximation of the model, an approximation between the relationship, an approximation of the relationship between inversion charge density and surface potential. That is, they are incrementally linear functions. It's a very good approximation that can be verified by measurement. By measurements is difficult because of space potential, but it can be verified from uh, other models, other accurate models, that are in function of surface potential. By applying this basic approximation to the differential form of the drain current and integrating this afterwards, we have the two saturation components as functions only of the inversion charge densities. Okay? Now I have to relate the inversion charge densities to the uh, terminal voltages, to the voltages VGB and VCB. And what we use then is the UCCM, Unified Charge Control Model, that was first presented by a Russian group, Sure and others. I don't know if you know them, but it was first presented by them as an empirical relationship. But I, ACM also showed no shown show that that applying the same basic approximation that was used before to the relationship of the expression of the electron concentration given by Boltzmann statistics and also to the charge sheet approximation. I won't show you the details because it's a little bit boring and I think at this time you are not interested in this. But applying the same approximation, we have a physical derivation of the UCCM model. And the UCCM model relates the inversion charge density to the terminal voltage. Okay? Then there's a parameter that appears here that is the inversion charge density at pinch off. It can be set arbitrarily, but ACM uses this value. It's a good value for the inversion charge density at pinch off. So we can have the voltage to current relationship just substituting you can see that the expression that I've shown first here, this one, I can invert this and express the inversion charge density as function of the saturation component of the current. Okay, and I did this here, and so here appears a normalization current, a specific current that is almost the same as an EKV model. It's the only difference is a factor 4. The ACM is times smaller than the EKV, but it also has the technological and the geometric information of the device. And so we can substitute this into the UCCM, and we have finally the single expression for the IV characteristic of the MOSFET in ACM model, which is very similar to the expression of EKV. You can compare both. We can compare the difference very little. I don't know if I put them together, but let's go back for you to remember. Square root and logarithm of square root, and also here I have square root and logarithm of square root, and so I can say that both models use the same relationship, almost the same relationship. The difference is very slight, and it's a function of this form. It's a function that must appear in many problems in engineer and other problems, isn't it? So you can find it in the literature. It's not inversible, but you can find in the literature, not only engineering literature, but other kinds of literature, numerical approximations for an inverse of this function. I suggest this one. This one is used in ACM. If you need this, not for hand calculations, sure, but if you need this, you can use. It's also analytical. It's a little bit cumbersome, but I think among the approximations I've seen in the literature is one of the most simple. Is one of the most simple, and they have a very good accuracy, even in moderate inversion for our case, where the error should be greater. It gives a good uh, accuracy. Now, just to finish our lecture today, let's show you the small signal the expressions for the small signal characteristics in both models. The transconductances are very similar. Also, the uh, intrinsic capacitances. Uh, as I told in the beginning of the class, we must have 9 different expressions for the capacitances, which are linear independent. Then we may calculate the other 7 to have 16 capacitance models, to have a charge conserving model that is still quasi-static. Um, but I will show here on the 5 more important ones. We don't give a charge conserving model, but are still good for hand calculation. And for EKV, we have something like this. Uh, we derive these expressions first by calculating the total charges in the device. The total charges are derived by integrating the charges densities. We have inversion charge density. We can have approximations for depletion charge densities in both models. Then we'll integrate this, and after integrating, we'll differentiate with respect to the terminal voltage to have the capacitance sure. But I didn't show how we derive this. I'm only showing the results. What I want to show you is that these equations here for ACM are single single for the whole inversion regimen, and they are functions of the saturation components of the currents. If you are working in saturation, which is the case of most circuits, we will must have the transistors operating saturation. The equations will be still simpler. Only 2 minutes. It's still simpler because the dependence will be on upon only one component, only on IF, which is also called the inversion level. It gives a measure of the inversion level of the transistor. I will talk about this in the next class. And I also finally show you an expression for the time constant of a first order NQS model. You can improve your small signal model by adding a denominator in the form 1 plus tau, this letter, tau s, okay, to your small signal parameters. And they are very similar. You can see that the difference is very, 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 very slight. Uh, in the next class, after talking about short chain effects, I will show you some circuits. Um, for ones we will analyze, for others we'll design the circuits, and we will use uh, one of these models. It does not matter which one because of their similarity. But for the secrets that should work in weak inversion, I will use the exponential asymptotic approach. But we can also use the general equation. And for other secrets, I will use the general equation, the equation that's valid in the whole inversion region. And we will see that the results predicted, the the performance predicted will be more um, accurate than if you have used a strong inversion model. Okay? And thank you for having so much patience with me. And the next class we will continue.